So up to this particular point on our tutorial, we're able to actually make use of that of the linear regression to actually solve this problem. Make use of linear regression. Remember, we actually make use of maths and paper to actually solve this. So what we're basically going to look at in this video is how to actually evaluate our linear regression model, because this is actually what we actually got, but we don't know how well the model is actually being performed. Remember, what I said, we are going to make use of thread based method to actually do that, which is actually mean squared error, and that of the mean average error, and that of the R2 score. So the mean absolute error, the mean that of the mean average error. These guys, the lower your value, the better how your model is actually going to perform. So, but remember that these three guys actually belong to that of the Scikit-Learn matrix, sub-matrix model on that of the Scikit-Learn. So we can actually put that. Let me actually get rid of this. Is actually the graph that we actually got in our previous video. So on top here, I can actually come here and say our what from our Scikit-Learn. For Scikit-Learn, that should be Scikit-Learn the what matrix. That should be actually a matrix. So I already have it copied, so let me actually paste it. So Scikit-Learn the matrix. You want to import this of our mean square error, mean absolute error, and R2 score. So but before we actually use this of the mean square error, mean absolute error, and this of the R2 score, we need to actually understand how these three guys actually work, the math behind these guys. So it's actually important to actually know all these guys. So by the end of this video, you are going to understand what this mean absolute error is, what the mean square error is, and that of the R2 score. So I have my WordPad open, so I'm just going to make use of example. So let's start from this of the can say mean squared error that we have here. We can actually name it as MCE. So the formula that this guy actually, when you look at it, is actually that of the square. So is that it makes use of that of the summation of what is actually the actual. When I mean the actual data, I mean we can set our actual to be, maybe our actual can be that of the initial y. So it's going to be that summation of that of the actual minus that of the predicted. By that I mean the predicted value, and there is going to be squared. Yeah, this is it, mean squared error. So, and this of the predicted from our linear regression that we actually did is going to be this of our y pred that we actually got error. This is going to be y pred. So let's actually go back. This is going to be our A, which is actual. P is going to be, I can say, the predicted. So it's going to be all divided by that of the n. When I mean n is number of observation. When I mean n, the total number of the prediction that was actually being made. Let's say your data set have that of the target, there's actually that of maybe 50 in number, so the n is going to be number of observation, which is going to be that of the 50. So actual minus the predicted square the summation and divided by that of the n. So like I said, our A is going to be our y. So our actual was this of the initial y that we actually said, which is this of the salary. The predicted was what we actually, which is going to be our y pred. So like that's why I make use of it to actually, so it will be easier for us to actually understand. So with this in place, this actually gives us everything that we need to actually know. Let's actually do. So let's actually look at example. Let's say in a station whereby we have the actual value was actually maybe something like let's assume 1, for example. The actual was actually 1 and the predicted was actually maybe 0, for example. And then okay, let's actually make, since this is a linear model, there's nothing like 1 and 0. Let's say the actual was actually maybe something like 2000, for example. This is 2000. Maybe the predicted was actually maybe something like maybe 3000, for example. So what it's going to do is going to be this actual value that we have here minus the predicted. It's going to be the predicted, and then it's going to what square them. It's going to square them. Then it's going to do all these things for all the or the predicted and that of the actually. So let's assume there's another one, maybe 1,000 for example, and then the predicted maybe something like maybe 1 2. So they are all going to be squared. We want to know what this summation actually does to actually sum up everything. So let's assume when we do this is actually this should be when you square them, the negative sign definitely go. This is actually going to be minus 1,000. When you square minus 1,000, negative sign is going to be actually being removed. So it's going to 1,000 times that of the 1,000. So let's actually go to my calculator. This is my calculator here. So I can actually say we know when we do this minus 2,000 minus 3,000 is going to be our that of the minus 1,000. So it's going to be minus 1,000. This is actually minus 1,000 squared. So it's going to be 1,000,000. And then it's still going to do the same thing for other ones. For this 1,000, it's still going to do the same. This is going to be minus 200 squared. Then after that, it's going to do the summation, and then it's going to divide it by the number of observation. So the lower your mean absolute mean squared error, the better your model is actually going to perform. We're still going to see how you can actually implement this. So when it comes to that of the let me get all these things back. When it comes to that of the mean absolute error, when it comes to let me actually get rid, they are basically just going to be saying okay. So the case is going to when it comes to that of mean absolute error. Remember this is actually mean absolute error. So this square root does not exist in that of this. So it's going to be divided by n. So this is trying to tell that a minus p is going to do it for all the predictions. Remember that not just one prediction. Let's say in our case here that we actually had that of the 5 predictions. So it's going to be the initial prediction. I think we actually predicted maybe something like 18,000. So it's going to be the true y is going to be 30,000 minus 18,000. 35,000 minus that of the 26,000, 40,000 minus that of the 34,000, and that of the we have this for 5,000 minus the for 2,000. Remember that this is actually what you predicted, so it's just basically the same thing. So 5,000 minus this of the 5,000, this guy is basically going to give you 0. So 0 squared, so same thing. So when we do this, then we can actually do after we are done getting all the output lined out, then we are going to sum each and every one of them. So this is basically what this summation to sum every one of them. So when we sum every all of them, so we are going to the output. Let's say assume that after we summed everything here, well, maybe something like maybe 150 for example. Let's assume 150. So the number of observation in our case here was actually 1 2 3 4 5. There are actually 5 numbers of observation, so we can actually divide it by what? 5. So we'll get our mean absolute error. For that of the mean squared error, basically the same thing, mean squared error. For that of the R2 score, this R2 score is basically different from this of the mean absolute error and that of the mean squared error. So what does this R2 score actually do? This R2 score is this actually like your model trying to how your model actually explains the variation on the data, on your data, like maybe when your data tend to actually variate, how well does your model actually explain this of the variations on that of your data. So this R2 score comes in that of the percentage. Percentage, the higher the percentage, the higher your model was actually able to explain the difference or the variation that happens within your data. So I think this actually explains it. For that of the R2 score, let me actually get rid of this. Okay, I think there should be something like cleaner here. So let me actually get rid of all this. How can't I make this big? Actually get rid of this. The R2 score is a little bit quite different compared to that of the mean absolute error and the mean what is it called? The mean squared error. Let me actually, why can't I make this brush a little bit maybe a little bit bigger? I think this actually settles it. Let's actually get rid of this. But they tend to actually make use of that of the same setting of the parameter, which is actually that of the actual and that of the I can say and that of the predicted. So I think this actually looks a little bit on our environment. So let's actually make use of this brush. So how does this root we can say R2 score actually work? This is actually when we mean R2 score is actually its R square. So how it works is actually make use of formula called 1 minus. Well, I think that should be x be xs. You can actually name it anything of your choice. So it is divided by that of the. Remember, this is actually a way is actually to explain. You actually to get the variation that happen on your data. You can actually that of the. You can say s total. I can say tolerance. Such as close this. So this xs ss that we have here, this s x can see this actually that of the s. So how is it actually represented? It's represented as that of the summation of that of the actual minus what are predicted, and then it's going to be squared. So and for this of the x, sorry, my environment is not that big. I think I can actually make it bigger. Now this of the xs dot is actually that of the given as that of the actual minus the mean of the actually the mean of the what actual. So this explains it all square. So let's actually put this. Let's actually put this here so we can close the braces. So this is the formula that this of the R2 score does. So it makes use of this to the summation. Remember that sorry, there's actually have to be a summation here. Sorry about that. Sorry for my handwriting. It's not looking really good. But when we look at this, we have that's this of the remember that this is just the variable I give it. This is actually that of the I say how to score the formula, make use of that of 1 minus that of the summation of that of the actual minus that of the predicted square divided by that of the summation of the actual minus mean of the actual. So this is not hard to actually understand. When we go to our data that we have here, let's assume the first one we actually have was this actual was actually this 30,000 and then the predicted was 18,000. So in this case scenario, so here is going to be 30 minus 18,000 squared. So it's going to do it for this of the 35,000 and minus this of the 26,000, which is actually the actual is the 35, and then the 26,000 was the actually the predicted. So it's going to do all of them squared. Then after that, it's going to find the summation. So after it's done finding the summation, let's assume everything ended up to be something like maybe 40. The 40, let's say it ended up being 40, and this of the R thought is going to be actual minus mean of the actual. So when I mean the mean of the actual or the actual, the mean of it. So the first guy was this of the 30,000. So it's going to be 30,000 minus the mean. So it's going to be 50, 45,000, 40, 35, 30,000 divided by number of observation, which is 1, 2, 3, 4, 5. We know that 5 is the number of observations. So it's going to all this guy divided by 5. The mean, that's how I actually get the mean. Well, after that, the actual minus. So it's going to be 30,000 minus the mean. Let's assume the mean was actually maybe something like maybe 40,000. So it's going to be 30,000 minus 40 minus mean of the mean minus 40,000. The 40,000 is actually that of the mean of the actual. So it's going to be 35,000 minus mean. There, so it's going to do all that. Then after that, let's assume that the our thought ended up becoming maybe something like, let's assume something like 20. The our thought is always let's assume it was 20. So it's going to be 1 minus this of the 40 divided by this of the 20. So it's going to do for. This is just the example that I'm giving does not mean this is actually the value that I are going to get. So 14 divided by 20 is going to be 20. 1 minus 20 minus 19. All this kind of just do this is actually the mass that this of the R2 score actually uses. But I remember that it actually calls in that of the percentage sign. So with this, we actually have a little bit knowledge on that of the R2 score. that of the what was the other one? The mean average error and that of the mean squared error. So let's actually see how you can actually implement this in that of the linear model. So remember that all of them make use of that of the y minus that of the y pred, y predicted, or can say actual minus that of the predicted. So this is the parameter that all of them tend to. The way you have to actually set it on this of the linear regression. So let's actually just implement that real quickly. So I'm not interested in drawing any graph here. So since we have actually we imported it, we imported it earlier. So let's actually come down here to run everything once and for all. So let's actually print this. So the first one we want to actually print is that of the mean squared error. So we are going to come here. Let's actually, let me just make it. So here is going to be our what? Mean squared error. So it's going to be the y underscore what? Y underscore predicted. So what did I say? What did I put underscore? This is going to be comma. So this is going to be the y true and the y predicted, like how we actually saw here. The actual minus the predictor, not actual minus predicted. So this actually used to be, why did I put this minus here? This is going to be comma here. So it's going to be the y true, that of the y predicted. So this is actually it. The y true was actually the data we actually gave it, which is actually the true data, and the y predicted was actually what we predicted. This is actually for that of the mean squared error. So let's actually do for that of the this is actually going to be that of the mean absolute error, and this is going to be our R2. So this is going to be R2 score. Simple as that. So it's going to be our mean, I think that should be mean absolute error, and then here is going to be our R, I think that should be R2 score. Thank you VS Code for helping me to actually bring out these guys. I don't need to actually type all of them from scratch again. So since we have all these guys, remember that the lower the value, the better. So remember that this guy actually comes that of the percentage 0.0 something. Let's actually run this to see that on our screen, to see that of the this of the mean squared error and mean absolute error, and this of the R2 score. Absolute error, mean squared error. There's actually many other metrics you can actually use to evaluate your model, but these three guys tend to do the job really well. They have that of the root. I think that should be root mean score. So I can't actually remember some of all these guys. I can't remember some of them. They are really much. When I mean these guys are really much, and they are quite hard to actually store in my head most of the time. So while this of the mean squared error, we're getting a large number here, which is not actually, you can see that our model was not actually performing well. We're getting almost 126 million points something, and then the mean absolute error are getting 8,004, and the R2 score .50, which just more like 50% 0.4. This is how well our model was actually able to explain that or the variations or things that happen within our data. So you can see how simple it was. This is actually the actually predicted, which is actually the y predicted, what was actually being predicted. So we check that of the mean squared error, mean absolute error, that of the R2 score. So I think with this explanation, with the basic explanation I've actually given you, with all these, some of the gibberish things that I wrote here, remember that this is actually supposed to be comma here, like when I was trying to explain how you can actually set it to that of the Scikit-Learn. So with this explanation, we're able to learn some of the key things that I can actually use to actually evaluate that of your, you can say, your machine learning model. Remember that this actually was for that of the linear model. I remember using making use of this is basically because linear models predict that of the continuous variables. You can say continuous values. That's what linear models actually predict. So You can't actually predict exactly the same stuff that linear model actually. Like let's say example like this, if it was a classifier or a classification based model, so you can actually predict whether if it's 0 or 1 by making use of that of the threshold, by making use of that of the sigmoid function. We are going to look at all these things in our next video, which we are going to make use of logistic regression. Basically, that's basically what we're going to look at in our next video. So make sure you check it out, because that's basically what we're going to look at. And it's going to be a little bit more interesting. We're going to see some other ways to actually evaluate that or the classification problem. Remember that most of the times, to me, I prefer that or the classification, even though the problem has to do with that of the regression problem. I still make use of that of the classification models to actually solve regression model. This is not actually advisable, but some cases they tend to perform even really better than this or some of these regression models. But don't take regression models for granted. Regression models can actually perform really well over that of the classification, depending on the problem that was actually given to them. So I think this actually concludes it. If you enjoyed the video, don't forget to subscribe. I'm happy to see you in the next one.